A solid conducting sphere is giving a positive charge Q. How is the charge Q distributed in or on the sphere? Well, the charge would be distributed on the sphere because the excess electrons would be distributed on the outer surface, because inside the sphere the electric field is 0. That's because there would be field lines that begin or end on excess charges, but there would be no electrostatic field within the body of the conductor, since there's no excess charge inside of it. Therefore, it's uniformly distributed on the surface of the sphere. Only two isolated charges, positive Q and negative 2Q, are 2 centimeters apart. If F is the magnitude of the force acting on charge negative 2Q, what are the magnitude and direction of the force acting on positive Q? So the first thing I did was draw a diagram of the situation. So positive Q and negative 2Q, since they have opposite charges, they would attract. So you could already cross out choices A and C. And then, according to Newton's third law, there are equal and opposite reactions for every action. So if F is the magnitude of the force acting on negative 2Q, the same amount of force would be acting on positive Q. So answer choice B, the magnitude is the same, F, and the direction is towards charge negative 2Q. The forces between two objects are inversely proportional to the square of the distance between the objects. Include which of the following? Select 2 answers. Well, you can use process of elimination here. Well, I haven't learned in physics 1 about nuclear force or magnetic force, so just thinking about it, I would cross those out. But then the gravitational force between two celestial bodies, I would use the force of gravity formula, because in the formula we have the gravitational constant times mass 1 times mass 2 divided by the radius squared. It has a similar structure to the electrostatic force equation, where the K times Q1 Q2 divided by the radius squared. They both have the distances that are being divided n squared according to the questions, which are inversely proportional to the square of distance, the radius. So choices A and B, the gravitational force between two celestial bodies and electrostatic force between two electrons. As you can see in the reference table, they have similar structures. Where's the other one? And up here. Yeah. Two small spheres have equal charges Q and are separated by a distance D. The force exerted on each sphere by the other has magnitude F. If the charge on each sphere is doubled and D is halved, the force on each sphere has magnitude. Well, this question, the first thing I did, I drew a diagram again, and I knew that I had to use this equation, and we could say this is a multiplier, so you could plug in 1 for K. You could plug in 1 for K, 1 for Q, and 1 for D. But since the charge on each sphere is doubled, the Q's would become 2, and the distance would become a half. So when you plug it into the equation, you get 1 times 2 times 2 divided by 1/2 squared. 1/2 squared is equal to 1/4. So then we'd have 4 divided by 1/4. If you flip, 4 times 4 is 16. And the force on each sphere would be 16. A circular ring made of an insulating material is cut in half. One half is given a charge negative q, uniformly distributed along its arc. If the other half is given a charge positive q and also is uniformly distributed along its arc, the two halves have then rejoined with an insulation at the junctions J as shown above. If there is no change in the charge distributions, what is the direction of the net electric force on an electron located at the center of the circle? So I drew an electron in the center of the circle. An electron is negatively charged, so it would move towards the positive end of the ring. So the answer choice B, towards the bottom of the page. It would repel the negative q side because the same charges, both negative, wouldn't attract to each other. Suppose that an electron charge, negative e, could orbit a proton, positive e, in a circular orbit of constant radius r. Assuming that the proton is stationary and only electrostatic forces act on the particles, which of the following represents the kinetic energy of the two-particle system? So for this question, we would use the electrostatic force as the force that keeps the electron in orbit. So we would use the Fe would equal the centripetal force. Yeah. So KQ1, Q2 over the radius squared equals mv squared over r. Looking at the answer choices, you would have to substitute K maybe later on with its constant value, the Coulomb's law constant, which is 1 over 4 pi dash. So we'll do that last. So we're going to solve, while we're doing this, we're going to solve for the velocity squared because they want to find the kinetic energy. So the EK equals 1/2 mv squared. So we're going to solve for the velocity squared. Okay. So K, using E as a thing. So E squared over the radius equals mv squared over r. I'm going to multiply by r on both sides. This is going to go away, and then there's only going to be one radius. So Ke squared over r equals mv squared. So we would divide the m out. So m would be over here. But I don't think the mass is accounted for in this equation. So we're going to make it equal to 1. So Ke squared equals, and then we're going to plug this in to this. So EK equals 1/2 the K. We're going to plug in the 1 over 4 pi that times this. Why did I make it so complicated? When you simplify it, it is 1 e squared over 2 times 4e the radius, which is choice A.